Hello everyone. Today I'm gonna talk about pendulum motion, and before I start it, let me quickly summarize the whole chapters, okay? Because this is the last section. So we start with the circular motion, right? So in general, we have a angle theta, arc length x, right? And then the radius is r, right? So then here we have the relationship between x r theta, which is x equal r theta, right? So this is our basic, one fundamental formula. So if you divide by t both side, left side is f v, and then r. The right side is going to be r times theta over t, which is omega, right? And then if you take the, if you divide both sides with t again, left side is going to be linear angle acceleration, and r alpha, where alpha is the angular acceleration, right? This is our starting point, right? And then we also talk about the relationship between frequency and time period. And then we also relate, omega, which is theta over time. Also, you can say this is a 2 pi period over, sorry, this is a 2 pi r over t, right? So then now you can say this is a 2 pi 1 over, sorry, 2 pi divided by t, right? And then this is also 2 pi times the frequency, right? So in other words, if we know omega, then we can find the t and f, or we can, if we know the other one of these, and then we can know the other two immediately. And then we can also define, function, simple harmonic motion spring, and this circular motion as well, and then a cosine omega t, right? And if we divide both sides and then take the derivative of it, that's gonna be velocity, and then that's a minus a omega, and then sine omega t, and then we can also divide both sides with t again, then we can have a acceleration, which is a minus a omega square and cosine omega t, right? So then, you know, you remember that the maximum value of x is a coefficient of a cosine function, which is a, and the maximum value of v is the coefficient of a sine function, which is a omega, and the coefficient of acceleration is a omega square. So the, oops. So then, let me quickly write the formulas. Right? So then, we have our x equals a cosine omega t. V is a omega minus sine omega t. And acceleration is minus a omega square cosine omega t. So we see omega a and a omega and a omega square is the maximum value of each of these, right? And the last time we talk about the energy, right? For the maximum kinetic energy is 1/2 times m v max square is equals to what? 1/2 times a times ka square, which is the maximum potential energy, right? So from here, we cancel, right? Left side is m, and the v max here is a omega square is k a square. So then a square cancel out. Left side is omega square is a k over m. So your omega is a root k over m, right? And then this is again 2 pi over t, or this is a 2 pi f. So you can basically express root k over m, for omega, and then period t, and then frequency f, right? That's what we did last time, right? And then now today we'll talk about pendulum motion, but you will see this is exactly the same as what I just showed you, right? So then now let's assume we have a pendulum. And then pendulum is, of course, mass is suspended from a pivot point by a light string or load. So here we said the light string, so that means the mass of string is 0. So then now you see we have a theta Ls. Again, the very first equation we had, right? We have an arc length x. Here is the S and the radius r, but instead of r, we have a length of the pendulum L and an angle theta again. Again, the relationship between these three is arc length is r theta. So in other words, here arc length S is a L theta, right? So basically the same. And then now let's assume we have a mass attached here, and then physics 1 and you learned the last semester said tells you you have to decompose this W force into two components, right? One is the horizontal force, which is a W cosine theta, and then the vertical force is a W cosine theta. So then you see tension and this W cosine theta will cancel out. So the F net force, horizontal force, is a minus mg sine theta only, which is this force. Again, W is a mg, right? So then we'll use called small angle approximation. So when the angle is small, sine theta is just almost the same as a theta. So here we assume theta is a radian. You cannot use degrees. So in other words, if theta is 0.1 radian, for example, sine 0.1 radian is actually 0.1, right? That's what it means. So now, assuming the pendulum angle here, theta, is a very small angle, then you can say instead of a theta, you can say your force is a minus mg theta. Well, theta, again, using the, this relationship, theta r and then x or s, you can say theta is a s over L. So then if you realize this force, that's simply this equation. And again, S is X, arc length, right? So then you see this type of a formula a few times earlier in this chapter. What is that? This is nothing but spring force. Remember, spring force is a minus kx. So that means this is your x. So then this mg over L corresponds to your spring constant for this pendulum motion, right? So this one is a K, right? So then now we come back to our formula set, right? So remember, I'm asking you, you have to, go over this process over and over by yourself, right? Instead of just, memorizing the formula. Again, how you have this formula. That's from the energy conservation, right? 1/2 times a Ka square, maximum, potential energy equals what? 1/2 times a mv max square, which is the maximum kinetic energy, but kinetic energy, the velocity maximum is a omega square, right? So you have to, again, you got to go over this process of, by yourself a few times. And then from here to here, this is exactly what I did like 5 minutes ago, right? You cancel, and then you cancel a square, a square. So then now you see omega is what? Root 2 k over m, right? And then from here, because omega is what? 2 pi f, right? So then you can say my frequency is a root k over m. And then if you move to pi, right? So it's 1 over 2 pi. That's how you get this, right? And then you can also solve this one for, period t as well. But now, for the pendulum motion, we already know K is a mg over L. So then now if you simply insert the K equals mg over L, so then your frequency will be changed root K over L, but K now is a what? mg over L. Then you can say cancel, then you see frequency is gonna be G over L. And then you can also find the period, right? So this is what you're gonna get, right? For the pendulum. Again, we have two different description for the frequency. Actually, three for the circular motion. For the circular motion or spring motion, circular motion, frequency is what? 2 pi omega, right? So omega, where omega is what? K over M, right? So then we express this omega is for the circular motion. And then we express omega in terms of K for the spring motion. So then now we express K in terms of GL for the pendulum motion. So basically you have three different version, right? Sorry, this is 1 over 2 pi, right? Three different version of a frequency, right? For the circular motion, spring motion, and then pendulum motion, right? Okay, and then again, think about you can also think about this one physically without the number. For example, frequency for the spring motion, you said here is a root to K over M. Again, why frequency is proportional to K? Because K, what is K? K is the stiffness of the spring. So if you have a stiff spring, the frequency, the oscillation of your frequency will increase, of course, right? But if you increase the mass of the spring, because if you attach, heavy mass there, spring will move back and forth slowly. So that means that your frequency will be decreased, right? That's why frequency is inversely proportional to mass. But now, think about the pendulum. If you have a gravity, strong gravity, the frequency will increase. Why? Because if you have a strong frequency of a pendulum motion, it will pull, the gravity will pull these motions faster, right? So that's why it's proportional to G. But if the length is longer, it will move slower. So that's why frequency is inversely proportional to L. So then now let's think about this question. When the pendulum is pulled to the side and released, the mass swings to the right as shown, right? So this is your starting point. This is your end point. The diagram shows position for half of the complete oscillation. So then now, because it's a half of because it moves here, and then another half will be here, right? It's not shown in the picture. So then at which point the highest speed? Of course, the middle point. Why? Of course, this is your speed zero, speed zero. So you have a maximum speed at the lowest position. So now you see, you can compare this one with the spring motion, even though this is pendulum motion, right? You have a spring here. This is equilibrium position. And then this corresponds to the maximum stretching position, this E, and then this position corresponds to maximum compression. So of course, your velocity is maximum here, right? With the spring motion. So this one is the same as here. And which point or points the acceleration is greatest? The acceleration A is greatest when? When the force is greatest, right? When your force is greatest for the spring motion, for example, because the spring force is minus kx, right? It's kx. So it's a maximum when x is a, which means at both ends, your acceleration and the force will be greatest. And which point the restoring force is great. Again, F equal ma. So if A is a maximum, F is a maximum as well. So they have the same location for their maximum values. And the second one is quite similar, right? When do we have an acceleration 0 now? Because again, force is a minus kx. When do we have a 0 force? Especially x equal 0. That is a equilibrium position, which is here and here, right? And then at which time kinetic energy maximum? Kinetic energy maximum equals to what? V max. Again, at the lowest position, B and D. When it's a potential energy maximum, whenever the ball is at the highest, so this is a AC, E. A ball of a mass, oscillating with a period, the T is a 2 second, right? And then if the ball released with another ball having twice the mass, the period will be. Again, don't simply memorize the formula. Again, you got to do this one, 1/2 times a Ka square, maximum potential energy. I'm doing this one, this is third time, right? Make sure you can do it by yourself. It's very important. mv max square, right? So cancel, left side Ka square, and V max is what? A omega square. So you cancel omega a's, so you have a omega is root K over M, right? And then now think about the small angle approximation. The left one is a minus mg sine theta, right? So that's a net force, right? But this case, we can have a small angle approximation. So now force is a mg theta. But again, we have a circular motion, right? This is theta r x, right? So then x is a r theta. So theta is a what? X over r. So then now you see minus mg, theta is a x over r. So then now you see this is k, right? So you insert this k value, right? K is a mg over r or L for the pendulum. You see this is a g over L. But now we 2 times over mass. You see omega is irrelevant to mass. So your period will be 2 seconds. Okay. And the same thing, very similar thing. Now we can use this formula again. Omega is root 2 g over L. Right? And then it says, you remove the planet, acceleration is half, right? So you have to express this omega in terms of a period first. Omega period relationship, omega is a pi over t, right? So that is a root 2 g over L. So then if you solve this one, upside down here, you see t over 2 pi, it's gotta be what? L over g, multiply 2 pi both sides, you see t is gotta be 2 pi root 2 L over g, right? So then now you see what happened. So this is a T1. So what is your T2? Everything same because we have the same length of L, but now G is a 1/2, right? So this is a G over 2, which is a 2 pi L 2L times G. Again, we separate root 2, which is a 2 pi root L over G times root 2, right? So this is what? T1. T1 times root 2. So you increase your period by factor of root 2. So the answer is 2 times root 2, right? Which is 2.8. And the next question, again, we will use the same formula. Omega is root G over L. right? Omega is root G over L, right? So then now we see again, from the previous question, we know omega does not depend on the mass, right? So mass, forget about it. And then we see it only depends on length of them, right? So then maybe the pendulum release, and then they begin to, right? So then what are you looking for? Which pendulum oscillates highest the frequency, right? So you have to change this equation in terms of frequency. Omega frequency has this relationship, and then your frequency is 1 over 2 pi G over L. So in order to increase frequency, you have to decrease your length. So the answer is A. And then grandfather clock you see here is nothing but what? It's a pendulum. So grandfather clock is designed so that one swing of the pendulum in either direction take 1 second. So what does that mean? When it goes back and forth, so 1 second, 1 second. So that means your period is 2 seconds. So what is the length of the pendulum? Again, your pendulum here, omega is root 2 G over L, right? So your omega is root 2 G over L. Again, you have to express this omega in terms of t, which is a 2 pi over t, right? So your t is a 2 second, so the left side is pi, equals root to g. We know g is roughly 10 over L. So you know this is a 3.14. So if you square both sides, the 3.14 square is roughly, I would say 10. Its right side is 10 over L. So then now you see that is a 1 meter. So this is the actual size of your grandfather clock, right? It's roughly 0.993 meters. Okay, guys, this is the last, lecture of the chapter 14. I think we relatively have long lectures, 5 or 6 lectures. But because again, physics, the very first step in the chapter is extremely important. Okay, so that's why I spend more time for these first chapters. Okay, and then we will do, we will start next chapter 15 next class, and I will assign the homework for chapter 14 as well. Thank you. And then your homework is due, next Monday.